Welcome to the beginning of the Web Application Hacking and Security Lecture Series. My name is Owen Redwood, and this is part of the 2015 version of the Offensive Computer Security courseware, hosted again at hackallthethings.com. The objectives for this lecture series is to A. become familiar with web application architectures and the security problems that plague them, understand the transition from what we've covered so far, binary exploitation, what we'll continue again with more later on, into now web application exploitation, and how I consider it really a subset of the former technique. And finally, to become familiar with the common web application vulnerabilities and the techniques that attackers use to exploit them, as well as the defenses used to prevent them. The outline for these lectures in this series are this lecture we're going to cover an overview of web application architecture and then dive into an introduction of client-side attacks, and finally touch on something that I'm a proponent of, meta-character injection theory, to classify the general category of web application exploitation techniques. Next lecture we'll cover OWASP, which is a big important resource for anyone doing web application security, and dive into server-side attacks. And then in lecture 103 we're going to cover SSL and the history of certificate disasters and failure. And 104 we're going to end talking about web application firewalls and how they're often more of a problem than they're worth. Here's a quick recap of all the topics we've covered so far. We've covered operating systems internals for Linux and Windows, and talked about rootkit design for both. We've talked about the whole spectrum of C and C++ security problems and vulnerabilities, ranging from buffer overflows to heap bugs to format strings, including a bonus lecture on type confusion vulnerabilities. We've covered x86 reverse engineering, fuzzing and bug hunting and vulnerability research. We've covered the basics of old school exploit development, and we'll resume that with the modern art of it after this lecture series. In that topic, we've covered exploit mitigations like DEP, ASLR. We've covered some networking so far, though it does deserve its own class for network security. We've covered TCP/IP basics, man-in-the-middle attack techniques, basic amplification techniques, and so on. So, the essence of web application architecture is that it is simply an extension of modern binary services over some very familiar ports, most notably port 80 and 443 for web traffic. There are a number of other services that exist to support these, like DNS and databases and so on, and they all play together behind the scenes to facilitate a user's experience on the internet. Now, how that actually plays out from the moment a user enters a URL in their browser typically begins with a query to a DNS server, assuming they, of course, have access to the internet. If they don't, then there's a bit more complicated routing techniques and protocols that will be engaged, ranging from ARP to whatever, to establish a link to a DNS server to resume that DNS query. Then finally, once the browser knows what the actual IP address of the target URL is, it will query it by connecting to it over either port 80 or 443 to some HTTP server. And that will be facilitated by a service like Apache, Nginx, Light HTTPD, which is common in embedded systems. Maybe legacy systems will be running Tomcat. And also you'll see Microsoft IIS on Windows servers. And each of these HTTP servers may be supplemented by various server-side scripting languages, ranging from the common PHP to ASP, to Java, Python, Ruby, Perl, even Go. And in order to do that, well, they have to have a corresponding interpreted language engine, as is the case for any scripted language. And that too is subject to vulnerabilities. And usually they are written in C and C++. And that is true for every single one of these examples here. The interpreter engines for these are written in C or C++, and thus are subject to, let's just say, interpreted language exploits that occur when memory corruption results from the incorrect implementation of the language's interpretation. And beyond that, there are other components that are engaged depending on the type of server. Maybe a database engine, some sort of file system access like LDAP or SOAP, maybe third-party authentication to content distribution network, content management systems maybe, and then any other form of third-party network content, most importantly being ads, as they host a lot of malware that most users never see coming. And there are scores of various HTTP browsers out there in terms of options for users, ranging from the big 3 or 4: Firefox, Chrome, Internet Explorer, Safari, or Opera, Dillo, Lynx, etc. For many Linux systems. And if you're interested in finding zero-day vulnerabilities in browsers, it's worthwhile to peruse this annotated timeline of browser development history across many distributions, showing which ones borrow components from others, like notably how WebKit plays into other browsers. And so each browser has its own unique termed browser engine, also known as rendering engine. For Chrome, it's Blink. For Safari, it's WebKit. For Firefox, it's Gecko, Internet Explorer, Trident, Opera, Presto. And all of these are also written in C and C++. And they may, again, be supported by client-side scripting engines to handle things like JavaScript, Python, ActionScript, VBScript, Dart, etc., as well as media player libraries to handle YouTube videos in Flash, HTML5, Netflix Silverlight, various auto codecs for streaming music and other content, and then finally scores of plugins. And this becomes very complicated on mobile platforms, as there's lots of malicious plugins out there. But I digress. There's script blockers, ad blockers, security plugins, plugins to find better prices when shopping, to block out content, to censor Kardashian nonsense, and so on. And also, there's password management, user data storage, bookmark synchronization, and all sorts of protections, policies, as well as user tracking and identification going on as well. So what does all of this mean, really? How do we boil this all down? The best way to explain this to a layman is that when they access a web page, there's a lot more going on behind the scenes, and their browser connects to a lot more different resources and interacts with a lot of different components internally than just the target website. And this is to query the DNS server, to parse the certificate information, to, on the server side, retrieve stored content from database server, as well as access media hosted on a CDN network, as well as to deliver advertisements to the unwitting user, and all this other third-party content. And both on the server side and the client side, multiple engines interact to facilitate all of this. And so, if you've never seen this before, it might be an eye-opener. It's really useful for teaching beginners exactly how the internet, or at least web browsing, all works. And it is 3D view in Firefox browser, and allows you to view web pages in a 3D form that shows you each layer going on. It may be iframes, it may be scripts, it may be images, and etc. It may be just URL links, and so on. But it at least shows you at least how much is going on, perhaps behind the scenes, that you don't see on web pages. And so this is Google without any query going on, and this is about 5 layers deep or so. And once you enter a query, there's advertisements going on, some involved with tracking you. There's advertisements between the results, and there's layers behind each result. It's quite big. And here's the second biggest search engine, Baidu, popular in Asia. And it has a similar layout with results and ads. Here's MSN, just loaded with content, videos, ads, media, things going off of the screen which may be never rendered to the user, which is very interesting because it can have scripts running in the background and doesn't necessarily have to be aligned or presented off screen to be invisible to the user. There are dozens of ways to do that. Here is QQ.com, another Alexa Top 10 website. There's a lot of layers going on. And here's Yahoo. Tons of layers going on. Here's YouTube. Tons of layers going on too. Or this is YouTube, rather. This one is by far the biggest with all the content it is displaying in layers, as well as all the analytics is performing or keeping on you, tracking what you watch and making recommendations to you. The takeaway from this is that on average, humans type 3 DNS queries per day, or 3 URLs per day. And for each one of those, there's over 500 on average different servers or different connections made to facilitate that. And this facilitates other forms of attacking. This is especially prevalent on mobile devices and tablets. It's clickjacking. It's a technique where layers are put above a enticing link. Maybe like you've won something, and then, or if you're streaming a movie or a video, there's ads in front of it. There's fake X's and stuff like that to trick you to touch it. This will trigger perhaps a malicious connection to a server hosting an exploit against your browser. And this is a wonderful statistic showing just how dangerous and relevant this is. The infographic is broken down by category with pornography, search engine, personal home pages, communication services, sites, businesses, etc., blogs, gambling, and then all other internet traffic. Now, of all the websites sampled from probably the Alexa 1000 that have been found to contain at least one malicious link, 22% of them were pornography sites, 16% of them were blogs, and so on. But in general, anything outside of porn, search engines, people's home pages, gambling, or blogs actually had the lion's share, which is all the other miscellaneous traffic reaching almost 40%. And these, again, are ads that may not even be present to the user. And they may involve malicious JavaScript, 0 days against any of the client's browser engines, either designed to handle the rendering, to handle third-party, media content like Flash or JavaScript or etc. And just from last year, there's been a 260% increase in malicious ads. And these are used to deliver ransomware like CryptoLocker, fake antivirus malware, fake Java updates, fake any form of updates, And you can read more about it on this link by Risk IQ. And a notable claim from it is that the rise of automated and programmatic advertising has really enabled this increase in malicious advertisements, because it's resulted in a huge M2M or machine-to-machine network, which they consider, and it's an apt description, an ecosystem of advertisements and tracking information. And it is often impossible, actually, for the services that host these ads to filter out all the malicious ones. And that's especially true for any advertisements that deliver zero-day exploits. And to give you some frame of reference for how deep this goes, there are several malicious ads found on the following domains. And this was put together by researcher Armin Pelkman, and found by surveying the Alexa 1000 malicious ads on, I think, the Alexa top 50 in Disney, Facebook, The Guardian, Amazon, even YouTube, Yahoo, and etc. And these, again, deliver a wide variety of payloads and attack types. The takeaway from all of this is that there is a 500-to-1 ratio of indirect interactions with other resources on the internet per single one made or initiated by a human user. This is a huge and hidden kind of interaction with the whole internet from users. It's a vector for malicious advertisements, for clickjacking, and all forms of different attacks. And this is again only how clients get attacked, and that's the theme of this lecture. But we're going to delve into server-side attack trends and so on just for a few slides right now. So, previously in the disclosure debate in Lecture 1, we talked about how many vulnerabilities that get disclosed, get patched, and there are a number of content management systems out there used to host, put together content on people's hosting servers, and these are abbreviated CMS, typically, ranging from Drupal to WordPress to etc. And in general, across the board, the CMS core developers are pretty good at patching the majority of zero-day vulnerabilities that are disclosed to them. However, there is a huge community for each CMS that deliver plugins to style Ajax, to style JavaScript, to style CSS, for making dynamic content more polished, etc., as well as providing analytics and statistics on user traffic. And these are a huge source of 0 days. There is a very, very small community that actually hunts for vulnerabilities in these CMS plugins, and it is an extremely low bar. It's very easy to find them. And the community as a whole is pretty bad at patching any of them that are discussed. It offers an interesting attack vector for any servers using a CMS. If a plugin can be detected by a malicious user, then they can easily find a way perhaps into it by bug hunting in that specific plugin. But I digress. Now, cross-site scripting attacks have been making a large rise in the community's statistics, and SQL injection has been going pretty steady. I don't have statistics for 2014, 2015, and again, this may not include zero-day attacks, so we're going to delve now into client-side attacks. This merges both server-side and client-side attacks, and we're going to split the lecture here to talk about these in more detail now. So, the average user has probably experienced some form of clickjacking attack. It requires novice skill to pull off just JavaScript or various layers. A obscuring a target link which instead hijack the user's click. Similar, cross-site scripting attacks try to hijack the user's resources, perhaps the session ID. And both of these can enable a number of different exploits, but a common one that's enabled is a attack that instead targets the web server, and this requires attacking the admin class of users of that website. And that's cross-site request forgery. It's known as, in other words, a one-click attack or a session writing attack that tries to exploit some malicious, unauthorized commands or features of a website from a user that it trusts, namely the admin. And again, someone sitting in a cafe sniffing wireless traffic can do this as well. And there's packet tampering, which enables other forms of web attacks and client attacks. And other types of attacks involve forged tokens, maybe copied tokens, or stolen rather. It's direct object reference, which may bypass various access control mechanisms, depending on how poorly they're implemented. There's SQL injection, which is a big attack technique that targets database information, and we're become very familiar with this style of attack. And there's directory traversal, which depends on the operating system hosting the web application, and in terms of what it takes to pull off. And then there's XML injection, and then there's the components that deliver dynamic content like Ajax, Flash, Silverlight, etc. And all of the core components are subject to zero-day vulnerabilities, and all of the client-side components are subject to vulnerabilities that can be delivered by these third-party components, as well as just any general content. And the takeaway is that the whole of web application architecture, from client to server, encompasses a huge attack surface, which involves many techniques to understand, to truly master it all. And that is one of the objectives really of this course, is to be able to understand all of this. And that's why we began with binary exploitation. So now let's dive into specific exploit techniques for client-side attacks. And to begin, we first have to understand HTTP. It is a stateless protocol that requires no handshakes, and at any time you can send an HTTP request about anything to a web server. It's also entirely plain text and comes with no cryptography on its own. That's what HTTPS is for. And HTTP is based on client requests and server responses, which both are headers followed by the respective request or response body. And HTTP requests must use a very specific request method. GET or POST are the common ones, where data is passed via variable equals value pairs, commonly with some form of delimiter to separate the various variables like commas. And the response from the server will use some form of status code along with whatever data may be corresponding to the request that generated it. Here's HTTP GET. This is an example of a client request, and it is known as the method that passes all the request data in the URL query string. And so the first line of a GET packet will be get the resource at the URL, so just /blog.php, and then it's going to define user as Bob, type as 1, and say that it is HTTP version 1.1. It's also going to tell it, your browser will typically tell it what browser it is, as well as what version it is, which tells anyone receiving this packet whether or not you're susceptible to vulnerabilities if you're running an old browser, which is a very, very common attack technique for fingerprinting victims. Post method passes all of the request data in the request body. So the first line of it will be the resource requested from the URL, so blog.php, and it's going to tell it the HTTP version. Now in the request body, it's going to tell it user is Bob and type is 1. And there'll be a tag in both of them saying what the content length is, etc. And so in response, there's 5 classes of errors. 404 is probably what everyone should be familiar with. It's the 400 series for client error. 500 series is interesting in most security cases because it indicates some form of server error. 300 indicates redirection. 200 is a success case and usually is not exposed to the user. And then 100 series is informational, usually doesn't indicate some form of error, but some information the client browser needs to know. Now, the common ones involve 200 for OK, which is usually corresponded by some form of data for the web page. 302 means the location has moved and it's going to be redirecting your browser to it. 401 means unauthorized. The client is not authorized for that resource. 403 is also forbidden. That means even with valid credentials, permissions forbid access to it. Usually it's a file system level. 404 means that resource does not exist, it's not found, so there's a client error for trying to access it. And 500 means internal server error, and that is perhaps caused by some form of internal component like a database failing. Now, how does it maintain state to track users, whether or not they're admins, guests, shoppers, what they have in their shopping cart, and etc.? Well, this must all be handled by the application designer. And typically, session IDs are passed along with the request, and those may be stored in cookies, or hidden form fields, or in the URL, which is a poor design choice. But these exist to associate requests within a single session associated to a single user. And this is all initiated with a set cookie header declared in a HTTP response, maybe from the user's first request or after they've clicked that login button and it actually went through. And so again, it follows the variable equals value pair and it's going to set what the cookie is, and the cookie will have actually various parameters that need to be set: the domain, the path, and then booleans for short-term, long-term, secure, HTTP only, and expires. The interesting ones for us are secure. It designates a policy that most browsers follow, I'm not sure if all of them do, to only send this cookie only over an encrypted channel like HTTPS, and not to one of the various third parties that are connected to upon any standard browsing for ads and etc. HTTP only prevents scripts from accessing the cookie, and only HTTP elements can access it. So this prevents JavaScript from accessing the cookie, and we are going to touch on this a bit later. These two together are extremely useful for any developers and should be mandatory in most cases. The domain and path settings are very useful for establishing where the cookie should be sent, as well as it is used for enforcing same origin policy, SOP. And so the domain, by default, if it's not set by the developer, will be set to the domain the request is sent to. And the path, if is not set to anything by default, but the developer can specify that this cookie is only for this subdirectory's worth of resources. Not subdomain, but directory. So say it's example.com/blog. The path, if I only wanted to send this cookie to resources under /blog, would then be set to /blog. Similarly, expires, short-term and long-term, are used for constraining the lifespan of the cookie, and short-term indicates that it is only meant to be stored in browser memory, so when the browser is closed or the tab is closed, that cookie now goes away. Long-term will store it on disk, which is important. So where it is stored differs depending on the browser as well as the operating system. And again, short-term cookies are ones that are only stored in browser memory and only are accessed during the actual communication. Since HTTP is stateless, it allows attackers as well as researchers and system administrators and testers to set up a proxy. In the next few minutes, we're going to go into a demo on this, but this allows us to intercept and tamper with arbitrary HTTP requests as well as server responses.
And this brings us to the HTTP proxy demo. We're going to be using Burp Suite, which is my current web proxy of choice. Burp Suite has a free edition, which does most everything you'll need for this class. There are some other good alternatives like Web Scarab and Mallory. Burp Suite and Web Scarab are both written in Java, I believe. And Mallory is written in Python, and I believe Mallory is open source and allows a bit more fine-grained control if you're familiar with Python. So I'm going to cover how to set up Burp Suite. Let's go to the top here and set up your web browser to point to it. So we're going to go to Firefox, Options, go to the Advanced, have the Network tab open. So here on the proxy, I have it checked to running. I've specified the IP address to be localhost, so I'm running this here locally. And I've specified that the port is going to be 8080. Now here on Firefox, in order to point it to it, on the networking settings, I have to specify to use a manual configuration, pointing it to localhost and pointing it to port 8080. Very, very simple. So I hit OK. And some other settings that you need to set up in the options is you need to specify when the proxy should intercept given client requests as well as given server responses for your target. So by default, this option will be on to not intercept any resource that has a file extension for something that's uninteresting, like a GIF or JPEG or PNG or something image related that doesn't really involve any interaction with backend components for the given website. And that's pretty safe to have on by default. However, what's not on by default is usually the AND URLs and target scope. That's very important so that if you're doing any other Googling or searching for research or vulnerabilities on the given target, all that traffic doesn't get blocked in the same proxy. So I'm going to, in a little bit, show you how to populate the target scope with the given target, and you also want to set the intercept server response to setting to have the same target scope match setting. Lastly, one of the most important options here that's usually on by default is going back to what I've said about fuzzing is for every fuzz test case that you generate, you need to have it be constructed so it passes the basic constraints. So if one of the variables in the file format or the request format or the protocol packet format is the length of the packet or length of the request or length of the file, every time you generate a test case, you need to set that properly because it's going to be the first thing that it checks. And if it sees that the amount of bytes that are in whatever this object are not the amount of bytes that are in this header, it's likely going to drop it right away and respond with some sort of error, not letting you explore or test any of the interesting code paths that it might otherwise explore. So by clicking automatically update content length header when a request is edited, and similarly for a response, when you go about editing anything you intercept, and forwarding it along to its destination, be it the target server or your web browser, it's going to update the metadata for the content link header so it passes that very basic constraint. So that's very useful. So let's go about setting it up so we can intercept with the proxy. And there are two tabs in the target settings. There's the sitemap and there's the scope. Right now, the only thing I have in the scope is something left over from an old demo, and I don't have anything for this website on the right. So in order to add the website that you're intending to go to your target scope, you're first going to have your proxy up, your web browser pointed to the proxy, set it not to intercept everything, you just go ahead and visit it. You'll see on the right that my sitemap gets populated with the URL I just visited. And so what you can do is you can right click and then you can do add to scope. And using a web browser, a web application proxy to inspect your general browsing habits is actually very, very useful and informative. For every website you'll see all the advertising traffic requests that your browser subsequently makes for visiting anything. You'll see all the cross-site requests for images, for resources, for scripts, and you'll be able to intercept those as well and inspect them. So that can be very useful for determining exactly how your information gets spread around. So what I've done is I've added the given website to the scope. You see it's encoded in a funky format. We're going to cover the ways these things are encoded in the next lecture. So what I'm going to go is to the proxy now and go to the intercept tab. And my intercept is off, so if I were to browse the website, it would not interfere with my ability to navigate the website. And if I turn it on, let's say I go ahead and try logging on as like admin, give it like password admin, I don't even remember, go away. It's going to just silently fail. So let's see what happens in this transaction. I've turned on the intercept. This is in my scope. And now when I hit login, my browser sends first the HTTP request to the proxy, and the proxy is going to forward it along. You'll see that the request is a post request. So that means that the information I'm passing along, the login name and the password is not going to be sent along in the URL. That would be get. Instead, it's sent in this. It's sent in the packet itself and the body of the request, and you can see here in plain text that user equals admin and it's delimited by ampersand, password equals admin. And so if anyone is man-in-the-middling your traffic and you're not using HTTPS, they will be able to see whatever your username and passwords are, just like this. So there are other tabs that allow you to see the data as well. This PHP session ID is simply just instilled from past browsing. But you can see that in the body there's the user variable and there's the password variable. There's other headers that are just broken down. The first thing I viewed was just the raw form. Hex is pretty straightforward. It's just this is what exactly is in the packet, the body of the TCP/IP packet. And so let's play around some. Let's go back, turn on intercept, and browse various pages to see what's going on. It seems that the other requests are GET requests instead of POST requests. And we're viewing all.php for all pictures. And so let's forward it. And we're going to forward that along to the server. The server is sending back its response. And you see here the HTTP status code is 200 and OK. You see here also the timestamp for this packet. It's also telling us very valuable information that it's running Apache web server, and that is version 2.2.16. It's also volunteering this information that's running PHP, specifically PHP version 5.3.3. Now with just that information, I could go search on ExploitDB or Security Focus or search the National Vulnerability Database for any CVEs or exploits for either Apache version 2.2.16 and or PHP version 5.3.3. Um, the other parameters it offers are encoding specifiers, which we'll cover next time, and also the content length, which I already discussed. And it's going to tell us that the content type is going to be plain text and HTML. So you see here in the server response is the HTML code for the web page. An attacker, if they had man-in-the-middle status, they could change things to whatever they wanted, insert whatever advertisements they have. And sometimes you'll find that internet service providers get caught all the time doing, instead of what the normal website is, inserting advertisements that make them money into your web traffic and altering your web traffic in similar fashion. I'm not pointing fingers at any particular internet service provider, however, I don't have any high opinions of any of them. So let's go ahead and forward this along and see what this looks like on the browser. Obviously, some things have changed. The title is now My Advertisement Here. And this form of man-in-the-middle power can be used for malicious advertising, for quote-unquote legitimate advertising, can be used for censorship and beyond. So it's important to be aware of. If this were, however, HTTPS, the attacker would not be able to have such power, or the man in the middle would not have such power. So let's see a different web site here. We're going to forward the request and forward it along, and we'll see that this is a blank page. Let's visit it again and see what is going on in this packet. It's requesting via GET request cat.php, and there's a question mark, and in PHP that specifies whatever comes after this are the parameters for the web page. So specifying ID of 3. Let's play with that. Let's do ID of 4 and forward it along. Let's see if it's still blank. Still blank. Let's do ID of 1. Forward it along. Now ID of 1 gives me something. You see that the URL is still the same. So if I were an attacker, I can redirect your request just like this. However, your browser, if I were to direct you to an entirely different domain, would likely not accept the response for this request from a different domain.
So the ability to capture, intercept, replay, and otherwise tamper with HTTP traffic is relevant for the majority of web servers out there. And here's a case to illustrate. Say a user accesses the web page and logs in over HTTPS. His credentials will be sent over an encrypted channel to the server, but however, the local network is Wi-Fi 802.11n or 802.11 or some variant thereof. The server will reply, sends a cookie to be set, dictating the session ID to use for the user. However, the majority of websites do not enforce HTTPS on every single page, but just for the logon page. And so subsequent visits, resource requests for the rest of the web page will be sent over HTTP, exposing the cookie and the session ID in plain text. And this allows the attacker who's sniffing to hijack the cookie, replay it, and hijack the session. It's trivial to pull off. And we've already covered one countermeasure to this. It's a cookie parameter. And so a question for you is, what cookie parameter prevents this from happening and prevents the cookie from being sent over HTTP? The answer is secure. It dictates to only send the cookie over HTTPS. Now, server side, there is another countermeasure that honestly should be standard on every single web server on the entire internet. Um, a lot of people think that SSL and TLS will have a huge performance impact on their infrastructure. Well, that may be if the engineers who designed it were utterly incompetent. Google decided to put the final nail in this coffin for this debate uh, 2 or 3 years ago when it decided to implement SSL and TLS mandatory in every single web page. The way to do this on the web server setting is something called HTTP Strict Transport Security. It's a header to force HTTPS on every single resource and to also, at the server side, disallow the access of any resource via HTTP. The response will be redirected to HTTPS, forcing the browser and the user to go through an encrypted channel. It's kind of the server side analog to the secure setting in the cookie parameter. So, with HTTPS on, the attacker must break SSL or TLS in order to pull off the attack. Holistically, the vast majority of websites out there are not secured against all of the attack types we are going to cover. Attackers can find multiple ways usually to access confidential data and gain unauthorized access to the website's internals, features, or systems. Attackers can use the vulnerable websites to, again, attack other users in a cross-site scripting attack or as a part of a larger campaign using a watering hole attack, which is common in APTs. And we're facing all of this because originally HTTP just was not designed to be secure. It was built for ARPANET, where it was a collection of universities and defense organizations owned by the government that were delivering static, read-only pages to be shared by researchers. There is no intrinsic security built in, no need for sessions or identifying users on the internet at that time, no need for dynamic pages or content or dynamic page support, and all of this modern content and stuff was really just bolted on later. That goes for the security as well. So, HTTP was not designed to support e-commerce and all these other important aspects of society: online banking, taxes, getting or filing for medical insurance or car insurance, accessing your medical data, and so on. But I digress. To understand cross-site scripting attacks, we're going to first dive into the document object model and how it parses markup language. The DOM, for short, parses all of the markup language in a web page that's returned in a HTTP response from a server into a tree format, where it parses the HTML tags and assigns whatever is contained within those tags into that object, and it is stored in a tree-like fashion with linked lists and so on. This allows a standard, in a sense, API for accessing all of the HTML objects of a document between, all of the interacting components that may be displaying, rendering, or otherwise changing the web page. And this includes the HTML rendering engine, say Blink, WebKit, or Gecko, or etc. The JavaScript interpreter engine, say V8 for Chrome, or etc. So the combination of DOM and JavaScript is where the heart of cross-site scripting really lies. With the DOM model, JavaScript is entitled to all the power it needs to create dynamic HTML. Now, this is designed to be innocent, but it allows JavaScript to generally be able to change all of the HTML elements in the page all of the attributes for any of the elements in the page, change any and all of the CSS styles as well as add additional ones. To remove existing HTML elements and attributes, add new ones, to react to any existing events or new events going on in the page, such as mouse over, clicking on objects, etc., as well as to create new events on the page. And this is documented further at w3schools.com here. And there is a number of details we're going to cover about how JavaScript and the DOM allows you to access the elements and cookies, and let's go through that list. So here's a list of methods to get elements. You can do document.getElement by ID, and then we'll use for reference the current document that the script is executing within. You can do get elements by tag name, so you can get all of the image tags, all of the forms, all of the tables, etc. You can get elements by class names, that's a little bit more specific. And you can change them by the following methods. The element.set attribute is kind of the standard way to do it, similar, as well as the dot attribute equals. And obviously you'd set the attribute name there as well as here. You can change the style of an HTML element, which may allow it to change how the CSS renders it or changes it. And then .inner HTML is pretty much guaranteed to always work as long as you can craft it correctly. You can add or remove elements rather straightforwardly with create element, remove child, append child, replace child, and you can just write directly to the document with document.write, and the text can have an arbitrary string containing an arbitrary amount of HTML tags in itself, which will then subsequently be interpreted and parsed into the DOM model. The following objects are a interesting topic to go over, especially document.cookie, which is the target of the majority of cross-site scripting attacks. Document.body allows access to the HTML of the document's body. The domain tells you essentially what the domain is that the HTTP request was sent to get this document. Forms, images, and scripts will return a list of the forms, images, and scripts. The URL, similar to the domain, will tell you what the URL was requested and refer if it exists or is populated. And script error checking will tell you if the if the settings on the essentially the debug options are turned on for running a script, which will tell you whether or not a script succeeded or failed in either running or loading, and so on. And this brings us to a very important topic. It's a defense that was built into browsers a long time ago to prevent cross-site scripting attacks, especially specifically scripts on page A from accessing objects on page B, especially if they don't have the same domain. But if they have the same domain, it may work. Specifically, the term is origin. An origin is consisted of a combination of the URI scheme, the host name, and the port number of the target server. If two web pages in two different tabs have the same origin, then scripts may access the objects of each other's paid documents. Otherwise, it is generally disallowed. However, this is not a perfect policy, and we're going to cover the ways that this falls apart and the ways to bypass this. SOP affects HTML objects depending on what their type is. For images, it will always show an image regardless of the origin, to the user, but it will not allow scripts executing on the page to access that content, especially when it's loaded into a canvas object. For scripts, this is the interesting case. The page will always run every script that occurs on it, which should raise a major red flag for any student. The one drawback that is humorous is that the document can't read the script's contents. For iframes, it's similar to images. The iframes will always be displayed to the user, but scripts executing in the outer frame will not allowed access to objects in the inner frame, the inside frame, and vice versa. There are many cases where SOP is too restrictive for large sites with multiple subdomains and many other examples. There are a number of ways to relax the SOP. Document.domain is one such technique. If two windows contain scripts, say from a single advertiser, that happen to set the document.domain to the same value, say tracking domain.xyz, say they're an ad service that likes to track every single thing that you do, then this SOP policy will be relaxed for these two windows, and the script on each page will be able to access, alter, and read every single object on each other's pages. And this goes across all tabs. And this is a common technique used by tracking services to essentially track everything you do. Enjoy learning that. Cross-origin resource sharing is a technique that was standardized and added as an extension of HTTP. It involves a new request header and response header. The request header is origin. The response header to that is HTTP access control allow origin. And this is allowed over HTTP. So the problem is that it is interceptable, spoofable, and yeah. Another way is cross-document messaging, which is something implemented in HTML5. It allows documents to communicate with each other across different origins or source domains. This method allows very crude security that has to be implemented manually. The way to do this is that the authors of the web services have to manually check the origin attribute from any accepted messages. Problem. So, JSON-P is another technique, and it stands for JSON with padding. And curiously enough, it's simply JSON including a script element. And this allows the page to run a script from any other domain and access all of the objects on that page, on that domain. So this bypasses SOP completely. And from Wikipedia, the quote is taken, JSON-P takes advantage of the fact that browsers do not enforce same object policy on script tags, within JSON. WebSockets, also implemented in HTML5, is a method by which modern browsers allow a script to connect to a WebSocket address, and SOP does not apply in WebSockets. Instead, a less sophisticated check is made that isn't run through the core SOP logic of the browser. And for WebSockets, the browser just inserts an origin header into any URI-based WebSocket connection made by the browser, but this can be potentially tampered with. And there are other corner cases. Pseudo protocols like JSON can implement their own weird things, and sometimes they don't necessarily have clearly defined host names or port numbers associated with their URLs, which will confuse SOP. Legacy cross-domain operations predating JavaScript, which is very, very rare, but post forms are included in this umbrella technically, though I haven't explored this, so this may be incorrect. Um, DNS rebinding and other server-side proxies tamper with the SOP identity, or otherwise the identity of an origin, and but this is very rare and limited. Um, the outcome here is that if the server-side proxy masks, say, an entire data center, and there's like 100 websites, they're all going to share the same domain potentially. Which brings us to cross-site scripting and other forms of malicious client-side scripting attacks. They effectively work as follows. First, an attacker infects a web page with a malicious script. The victim then visits it. The script is injected into the HTTP response that the victim gets from the request, and upon rendering the response, it executes the script, which accesses another website, a third-party domain, which hosts some evil script, causing the browser of the victim to do evil stuff. There are two types of this attack. First, reflected, which is termed non-persistent. It is either injected into the traffic, into the HTTP request or query or stream. And finally, stored cross-site scripting, otherwise known as persistent. Happens when the web page saves the XSS attack into the database or some other form of persistent storage. Now, interpreted languages typically have two categories of input. This is going up to a higher level, talking about this in abstract form. Data and syntax. These two categories dictate how interpreted languages parse their inputs. Syntax typically changes how the data is parsed. In other words, it may tell it that, hey, the rest of the data between these two syntax tags treat it as script or some other form of command. And there are all forms of syntax characters that may exist depending on the given engine. Brackets for markup languages, slashes for file systems, and dot dots, and so on. The problem here, as with binary exploitation, is that the mixing of code, data, and user input in the same context, the system simply cannot distinguish without extra developer additions between them all. And so the problems arise when hostile input is then parsed by an interpreter. So the developer's job is to prevent any input from being parsed by an interpreter, which is difficult, especially in complex web pages. JavaScript is typically begun with a script and ended with a slash script tag. It's a very basic language that I'm not going to give a great overview of because of the time limitations and how also easy it is. You could do it in a weekend and become a master with probably Khan Academy, but I digress. Script, alert, and some text message here is the typical way that XSS vulnerabilities are tested. And malicious JavaScript here can access the document's cookies, history, settings, etc. It can download files, it can redirect a user to a phishing website, it can deliver exploits, O-days, N-days, etc. Here are some basic examples. Again, the script alert test is a very common one that's very harmless to attempt on web pages. Again, you are not legally allowed to test this on any web page without permission, which is why it's useful to test it at home on virtual machines, or at cloud testing sites that allow such activity. But I digress. The main reason that they're not allowed is because they may be stored vulnerabilities, which then would hit other users. If it's reflected, it's only going to hit you, potentially. But it may not. It really just depends on how poorly the website was engineered, which is impossible to know really remotely. A second example is one that accesses cookie. alternative to the script generic tag, you can do it within an image tag and using a HTML event. For instance, providing an invalid URI for a image or a media file, and then providing a HTML uh, event for the error upon the error of not loading this, perform the following JavaScript. This would be a second example of a cross-site scripting vector, one in this case that alerts the user of what their cookie is actually set to. Now, this could, instead of alerting to the local user, send document.cookie off to another resource by some form of URI request again, or so on. Now, this third example shows a similar vector that on the error creates a element that will run, and it will access a JavaScript file to run from this given URI, so it's a remote file potentially, and it will append it to the current document's body, which will cause it to be rendered and allow it access to the document's objects potentially. OWASP provides 8 rather trustworthy rules to follow for a developer who wants to prevent cross-site scripting attacks on their web page. Number 1, never insert untrusted user input into your persistent storage, database, etc., except in allowed locations. And in such a case, do all the following. 2, HTML escape before inserting user input into HTML elements. 3, attribute escape before inserting user input into HTML attribute values. 4, JavaScript escape before inserting user input into JavaScript values. 5, CSS escape and strictly validate before inserting user input into style properties. 6, URL escape before inserting user data into URL parameters. 7, sanitize HTML markup with the library designed for the job, which requires a little bit of research. And 8, prevent DOM-based cross-site scripting. And these are all spelled out in more detail at owasp.org, which is a resource that everyone should be aware of in web development. Now, there are ways to bypass this. Some of these filters. For filters that filter out script, you can instead embed them in image tags. For filters that look for quotes and semicolons and filter those out, there are ways to get around that as well. Or with grave accents, which are using other character sets, and these are accents that are treated as semi and single, quotes and semicolons. For case-sensitive filters that are looking for, say, all lowercase JavaScript, etc. And for malformed tags, you can attack a tag and image tag and such, and you can always render XSS or any script or any character with the function from car code, which is a way to write essentially raw bytes into JavaScript, which is typically done at post-processing in terms of post or after the filters, which is fun. Because most filters are done at the point of first processing user input and not then running it. Now, you can do all of these recursively, and this will be single pass filters or n pass filters, depending on how large n is. And so the solution defensively is to do all of these recursively. First, at the processing of user input, and then at the calculation of do it recursively at user input, and then do it recursively before calculating and composing the HTML response. That is essentially the proper way to do this, which is something that is never taught to developers, at least in school that I've seen. These are some generic catch-alls that are useful for testing. All they do is alert XSS, but combine all of the techniques really to do it. The second one requires viewing the source, and these are provided at OWASP.org on their filter evasion cheat sheet. And this all brings us to a wonderful theory that I've come up with to teach all of this, all of web application hacking and security. It boils down to an extension of binary exploitation, specifically fuzzing. This alteration of fuzzing I term meta-character injection. It has two requirements: two categories of user input, data, and syntax. The syntax may be used in the interpreted language to tell the parser to, hey, now interpret the rest of this as script, or code, or etc., or commands, until the following ending tag /script, or so on. And then finally, the user input involves mixing of code and data. Then the methodology is threefold. Enumerate the web application architecture components, both on the client side and the server side. Enumerate all of the syntax characters for all of these components. Simply add it to your mutator or your dictionary for what you want to mutate with. Sometimes you want to use combinations of multiple syntax characters. For file inclusion and directory traversal, you'll want ... Then proceed with testing the applications and the architecture as if you were fuzzing it. The web server typically will interact with multiple components, which is why this will potentially trigger errors and vulnerabilities in multiple of the backend components that you can't directly test. That is why this methodology is very effective, and we use it here at Hack All the Things and other workshops. And while we're on the topic of modern binary exploitation and fuzzing, let's talk about how JavaScript can be used to heap spray and pull off binary exploitation attacks against one's web browser. With, say, Chrome ODAs, Firefox, IE, Opera ODAs, etc. The original technique, invented back in 2004 or so by Blaz and Skyline D, or Skylined, was simply just the allocation of a new array and then iterating through each element and filling it with some pre-defined NOP and shellcode strings. It's really just that simple. It's going to allocate them all in the heap in a very deterministic manner. To illustrate, these slides are from Alex Sodorov's Black Hat 2007 presentation titled Heap Feng Shui in JavaScript. This would denote a typical heap with some used memory chunks. And with this heap spray, the following chunks would be allocated in a very deterministic manner. And previously I've talked about the address 0C, 0C, 0C in terms of heap exploitation, as it's a common target to overwrite or return address with to jump to. As with this technique, it's very likely to contain shellcode, at least if there's no ASLR going on. So for more resources, the following two links should provide you with plenty of information to get started exploring how to pull off a heap spray and heap-based attacks in browser exploitation. Now, to go back to web application hacking in general, let's revisit the same origin policy and talk about two examples at the network level that an attacker could go about bypassing it. First, many websites do not run their own DNS server and do not use a DNS server that enforces DNSSEC, which allows an attacker to spoof DNS records, at least at the ISP level, for a fake subdomain of a given target website. The second step would be to infect the target website with a script spoofing the same domain, pointing to a script at this fake subdomain, say, for instance, dev.example.com, where otherwise there would be actually no dev.example.com. But the attacker could come up with a variety of innocuous sounding subdomain names that would cause a company to think not even think twice. Then the third step here is the victim would then visit the web page. It would get the injected script and the HTTP response, and then the script would download from this third-party server that the attacker has set up to hold this script at dev.example.com, and then we would run within the context of the target web page, example.com, and be able to access all of the objects, say the document.cookie, and etc. A second example for when there is a target network that does have a DNS. This shouldn't be a public DNS, but a private DNS working, and you want to attack the target networks or the company's employees or users. If they have a poorly managed firewall and poorly managed DNS, and the firewall allows DNS updates in over the network, then the attack would be the exact same. The attacker would spoof DNS records for a fake subdomain, and the rest would follow this exact same way. So the defenses a user or client can engage in primarily involve blocking JavaScript and downloading a script blocker, as well as an ad blocker. And the quality and efficiency really varies a lot among the options, from no script to script safe and etc. And always keep it on. Now, server-side precautions involve obviously HTML escaping, the various cross-site scripting filters. We've talked about. And so on. And you can always read more at owasp.org about cross-site scripting. And that concludes today's lecture. Next time, we'll cover server-side attacks and more from OWASP.